Hey everyone, welcome to This Explainer. Today, we're diving into something that is literally the absolute backbone of modern decision-making, and that is data. But here's the thing about raw data, right? It's exactly like raw cooking ingredients. Imagine you've just got this massive pile of unpeeled vegetables and raw flour sitting on your kitchen counter. I mean, it's not a meal yet. It takes prep work, the right techniques, and a little bit of artistry to turn those raw, chaotic ingredients into an actual masterpiece.
So that brings us to a pretty massive question. How do we actually make sense of overwhelming amounts of raw data? Well, we need a recipe. And in the world of data science, that ultimate recipe is a combination of descriptive statistics and data visualization. These are the exact tools we use to transform those chaotic, endless rows of information into crystal clear, actionable insights.
Okay, let's dive into this. Here's our roadmap for today. We're going to cover data, variables, and features first. Then we'll look at measures of central tendency, followed by measures of dispersion, and finally, we'll wrap up by visualizing both numerical and categorical data.
All right, let's jump right into Section 1, Data, Variables, and Features. Think of this as gathering our fundamental raw materials.
You know, whenever we collect information, it generally falls into one of two major buckets. On one side, we've got structured data. This is your highly organized, quantitative stuff. It fits absolutely perfectly into neat little tables and relational databases, which honestly makes it a total dream for machine learning algorithms to search and analyze. But then, on the other side, we have unstructured data. And this is the messy, complex, qualitative stuff. Think text documents, images, videos, the kind of stuff that doesn't have a predefined model. So it requires a lot more heavy lifting to actually organize and understand.
So let's break that down even further. Qualitative data captures non-numerical concepts. It can be nominal, meaning we just use unique labels with zero hierarchy like gender or hair color, or it can be ordinal, which involves a natural ranking. Think of a customer satisfaction rating from 1 to 5, right? Then we have quantitative data, which are the numbers we can actually measure. This can be discrete, meaning specific, countable, distinct values, like the exact number of cars parked outside, or it can be continuous, which represents measurements that can be infinitely broken down into decimals, like your height or the exact temperature outside.
And this brilliantly illustrates what structured data actually looks like in the wild. We're looking at a loan application table here. Notice how gender represents our nominal qualitative data, credit history is our ordinal data, since there's a ranking there, and income serves as our continuous quantitative data, because we're dealing with specific, measurable monetary values that can vary endlessly.
Now, in data science, we actually call these different data columns variables or features, and every single feature contributes to our understanding of whatever phenomenon we're looking at. But they're not all doing the exact same job. We split them up. We have independent variables, which are also known as predictors, things like income and credit history. And then we have the dependent variable, which is our target. So in this loan scenario, our ultimate goal is to use those independent predictor variables to figure out the final dependent target variable, loan status. Basically, will they get the loan, yes or no?
Okay, now that we've gathered our raw ingredients, let's move right into Section 2, Measure of Central Tendency, or in simpler terms, finding the center of our data.
Measures of central tendency basically give us a single, typical value that represents the entire data set. We have three main tools we use for this. The mean is simply your standard mathematical average. The median is the absolute middle value when you literally line all your data up in order. And the mode is just the most frequently occurring value, which, by the way, is incredibly helpful for categorical data when you really just want to know the most common group.
Now, what's really interesting about this slide is the hidden danger of relying strictly on the mean. So, in a normal data set, the mean and median are usually pretty close to each other. But look what happens if we introduce a massive outlier. Imagine in year 10, someone suddenly earns $19,000. That single extreme value violently yanks the mean upward, completely skewing it, and giving us a totally false impression of what a typical salary is here. The median, however, it stands its ground. It just ignores the extreme edges and stays right at 7,210. So when outliers are crashing the party, the median is a much safer metric for finding the true center.
So we know where the middle of our data is. But what if the rest of the data is scattered wildly all over the place? Well, that brings us to Section 3, Measure of Dispersion, which is all about the spread of our data.
Let's take a look at these two temperature tables over a 7-day period. For both tables, the mean temperature is exactly 20 degrees, but honestly, their story is completely different.
The data on the left tightly hugs that mean, just hovering right around 19 to 21 degrees. We call this low variance. But the data on the right? It swings wildly, dropping all the way down to 11 degrees and then spiking up to 31. That is high variance. If you only looked at the mean, you'd think both weeks felt exactly the same. Dispersion is what tells you the real weather story.
To actually quantify this spread, we use some specific metrics. Variance gives us the average squared differences from the mean. But if we take its square root, we get the standard deviation, which is much more intuitive to use. It just tells us the average distance our data points sit from the mean. And, just like we used the median earlier to avoid those crazy outliers, we can use the interquartile range, or IQR. The IQR measures the spread of the middle 50% of our data, effectively just ignoring those wild extreme values hanging out on the fringes.
All right, we have our data types, our centers, and our spreads. It's time for the grand finale of our building blocks journey. Let's get into section 4, visualizing numerical data. This is where we map the numbers.
First off, let's be super clear about something. Visualizing data is not just about making pretty pictures for a board presentation. It is arguably the absolute most powerful analytical tool we have. Visuals reveal hidden patterns that raw numbers just obscure. They let us communicate incredibly complex mathematical findings to non-technical stakeholders instantly. They make outliers literally pop off the screen, and most importantly, they empower leaders to make informed, strategic decisions based on actual reality, not just guesswork.
Let's move along and see how this builds visually, starting with the histogram. This chart is brilliant for continuous data. What it does is take a wide range of numerical values and groups them into sequential buckets or bins. Think like values from 0 to 2000, then 2000 to 4000. The height of the bar shows you the frequency of data points falling into that specific range. It gives you this amazing instant feel for the underlying distribution of your whole data set.
Next up, we have the trusty bar chart, which is absolutely fantastic for discrete numerical values. Unlike the histogram, which uses those range bins we just talked about, here each individual item gets its own distinct bar. Because the heights are mapped directly to values, it's incredibly easy for your brain to scan across and spot the absolute highest and lowest individual values in just a fraction of a second.
And then we have this chart. Oh man, this brings our entire explainer full circle. The box plot is an absolute masterpiece of statistical visualization. Remember all those concepts we were just talking about? This one single chart shows them all at once. That line right in the middle of the box, that's our median. The actual height of the box itself, that perfectly outlines our interquartile range, capturing that middle 50% of the data spread. And those little dots sitting way up top outside the lines, those are our outliers, explicitly identified and separated from the typical data. It's literally central tendency and dispersion all wrapped up in one graphic.
Okay, before we wrap up today, let's shift gears slightly to section 5, visualizing categorical data. This is how we handle qualitative groupings. When we aren't dealing with continuous math, but rather discrete groups, we turn to these tried and true methods. We can definitely still use bar charts, but this time we use them to show the frequency of a category. Like, say, how many married versus unmarried applicants are in a dataset. We use pie charts when we want to show relative proportions compared to the whole. And guess what? We can even use our beloved box plots to compare multiple categories side by side. For example, you could plot the income spread of men directly next to the income spread of women just to quickly see the differences in their medians and variances.
And that brings us to the end of our recipe. We've gone from messy, raw ingredients to a highly structured, understandable visual feast. So I'm going to leave you with this thought. Next time you see a chart in the news, or you're looking at a dashboard at work, are you just going to take it at face value? Or will you look a little closer to see if a massive outlier is secretly skewing the mean? Will you check if the invisible spread of the data is actually telling a completely different story? Thank you so much for joining me on this explainer, and remember, always keep questioning the data.